Namaste. This is the week of for introductions and we shall recap many of the formulae that you already know. This way everybody is on the same platform for better understanding of the topics. A triangle is a plane figure with 3 sides and 3 angles. Its perimeter is the sum of the lengths of the 3 sides. The area is half of base length times the height. Now, how do we figure out the height? A triangle is a plane figure with 3 sides and 3 angles. Now, let us draw a triangle. Suppose this is a triangle that we refer to as A, B, C. Now, these sides have lengths of small a, small b and small c. The perimeter of a triangle is the sum of the lengths of the 3 sides. So, P or the perimeter equals A plus B plus C. The area of the triangle is half of the base length times the height. Now, suppose we take the base to be BC. So, your base equals BC. So, how do we find the height? We take point A and we draw a perpendicular to BC. Suppose it intersects at point D. Now, the length AD is equal to H. So, the area of the triangle ABC would be equal to half of A into H, and you can do this for any of the other sides as well. An equilateral triangle is a triangle in which all the 3 sides are equal and all the 3 angles are 60 degrees. So, if we draw an equilateral triangle, we will have all these 3 angles as 60 degrees and all the sides are of the same length. Suppose we call it as small a. So, its perimeter would be a plus a plus a or thrice of a, that is 3 times the length of a side. The area of an equilateral triangle can be found by using this formula: A equals root 3 by 4 times a square. A rectangle on the other hand is a plane figure with 4 sides and 4 right angles. Now, suppose we call this rectangle ABCD. Now, it has got 4 sides. AB is equal to CD and both of these are parallel, that is AB is parallel to CD. Similarly, AD is equal to BC and AD is parallel to BC. So, the opposite sides are equal and the opposite sides are parallel. All the angles are 90 degrees. Now, suppose we call CD as having the length L. So, AB will also be having the length L. If we say that BC has a height of H, then AD also has a height of H. The area is equal to base into height, that is L into H. The perimeter will be equal to AB. So, perimeter equals AB plus BC plus CD plus DA. AB is L plus H plus L plus H equals twice of L plus H. So, the perimeter is twice the sum of the lengths of sides and the area is the product of the lengths of sides. Let us consider the next figure. It is a circle. Let us draw a circle. So, a circle is a plane figure. It has a center that we represent as O and all the points on the circle are at the same distance r from the circle from the center. So, this is r, this is also r. The diameter is a chord that, so it is a line that passes through the center and it cuts the circle at 2 points A and B. Now, diameter is twice the radius, the perimeter is given by 2 pi r, and the area of the circle is given by pi r square. Now, why do we need to know about a circle? Many trees, especially coniferous trees, have a circular cross section. So, suppose we have a tree and suppose this cross section is a circle. Now, if we know the circumference of this circle, we can find out 2 pi r. Now, how do we find out the circumference of the circle? Well, we can use a tape. So, you take a tape, move it all around this circle, and the length of that tape will give you the perimeter of the circle. Alternatively, you can use calipers. So, when you use calipers, you can put one end of the caliper at this point, the other end of the caliper at this point, and you can figure out this length, and this length will be equal to d. So, either we can find out 2 pi r using a tape, or we can find out d using calipers. Now, in both these situations, if you wanted to figure out the basal area, that is the area of this circle, you can do it. So, suppose you know this 2 pi r equals a length L. So, that would imply that r equals L upon 2 pi, and the area, which is pi r square, will be given by pi into L by 2 pi square. Alternatively, if we knew d, we know that d equals twice of radius. So, r equals d by 2, and the area or the basal area would be pi r square equals pi d square by 4. So, in the case of coniferous trees, we can very easily find out the basal area either by using the perimeter measured with a tape, or by using the diameter as measured with calipers. The next figure is called an ellipse. Now, an ellipse is a plane figure in the form of a regular oval. So, it has got two origins, let us call it O1 and O2, and all the points on this ellipse are such that the length L1 plus L2, every point A on this ellipse to these origins O1 and O2. So, if we so in the case of an ellipse, L1 plus L2 is a constant. At the same time, an ellipse is said to have two axes. So, this is called the major axis, and this thing is called the minor axis. Now, major axis is generally represented by twice of A, and minor axis is represented by twice of B. So, half of the major axis is A and half of the minor axis is B. The area of an ellipse is given by pi times A times B. Now, why do we need to know about an ellipse? Well, because again many trees have elliptical cross sections. In the case of a tree that has an elliptical cross section, you can find out which side has the greatest length. Suppose this has a length of say 20 centimeters, and on the opposite end, if you measure across the minor axis, suppose that length comes to be 10 centimeters. So, now you can figure out the basal area of this tree. A cuboid is a solid figure. It has 6 regular faces at right angles to each other. So, let us draw a cuboid. So, now this cuboid has got 6 faces: A, B, C, D, A, B, E, F, E, F, G, H, GHDC, BFGC and AEHD. So, it has got 6 faces. The opposite faces are parallel to each other and the faces that are adjacent to each other are at right angles. A cuboid is said to have a length, a breadth and a height. The volume of a cuboid is given by length times breadth times height. The area of a lateral surface, so suppose we consider a lateral surface as BFGC. Now, because a lateral surface is a rectangle, so its area would be given by its length times the height. So, in this case it is L multiplied by H. The area of the lateral surface of the cuboid is given by the sum of the areas of the lateral rectangles. The area of the end surface is the sum of the areas of the end rectangles. The total surface area is the sum of the lateral surface areas and the end surface areas. The next solid figure is a cylinder. Now, you can construct a cylinder by taking a circle and moving it perpendicular to the circle. Now, if we move this circle on this direction and suppose it reaches at this point, so this is a cylinder. Alternatively, you can construct a cylinder by taking a rectangle and rolling it so that both these edges E1 and E2 get jointed together. So, a cylinder is a solid geometrical figure with straight parallel sides and a circular or an oval cross section. The volume of a cylinder is given by the basal area. So, because this is a circle, suppose it has a radius of r. So, the basal area is given by pi r square. The volume is given by multiplication of the basal area with the height of the cylinder. So, the volume is equal to pi r square h. Now, suppose we wish to figure out the lateral surface area. Now, the lateral surface area is this surface area, the surface area that is on the sides of a cylinder. Now, the lateral surface area is given by the circumference of this circle multiplied by the height. So, the lateral surface area is 2 pi r into h. The end surface area, because this is a circle, it is given by pi r square. So, the total surface area of a cylinder is given by pi r square plus pi r square for the two ends plus the lateral surface area is 2 pi r h. So, it becomes 2 pi r square plus 2 pi r h, or we can also write it as 2 pi r bracket h plus r. So, this is the total surface area of a cylinder. Solid figure is a cone. So, a cone consists of a circle and all the points are made to taper to a single point. So, it has a circular base which has a center O and a radius r, and it has a height that is given by h. So, if the height of the figure is h and the base has a radius of r, then we can find out the slant height. Now, slant height is this length, it is given by L. Now, L can be very easily figured out by using the Pythagoras theorem. L square equals r square plus h square. The volume of a cone is given by 1/3 of the volume of a cylinder of similar radius and similar height. So, the volume would be given by 1/3 pi r square h. The area of the lateral surface, so the lateral surface area is given by pi r L, and the area of the end, because it is a circle, it is given by the end surface area equals pi r square. The total surface area then is given by pi r square plus pi r L equals pi r L plus r. The next solid figure is a sphere. So, similar to a circle, a sphere consists of a center O, and it consists of all the points that are at the same distance r from the center in the 3 dimensions. As in the case of a circle, here also we can define diameter as twice of the radius. The surface area of a sphere, the surface area is given by 4 pi r square, and the volume of a cylinder is given by 4 by 3 pi r cube. Now that we know about these plane and solid figures, let us have a look at some practical problems from the field. Calculate packing density of trees for square packing and hexagonal packing as depicted in these figures. It is important if we wish to have the highest number of trees per hectare of the forest. So, how do we calculate a packing density? Suppose you planted trees in a regular grid, and this is a rectangular grid. So, later on this tree will have a canopy like this, the next tree will also have a canopy. Now, because all these trees are of the same species and at the same site, so this packing would become a square packing. Now, we wish to figure out how much of the area of the land is covered by these canopies. So, how do we do it? Consider just 4 points, and we have circles there, and these circles are touching each other. These are their centers. Now, consider this length. This is r, this is r. So, this total is equal to 2r or d. Similarly, this side is d, this is d, and this is d. So, in this case, if we consider this square, that is a b c d. So, a b c d is a square of side d. So, what is the area of ABCD? It will be given by d square. Now, if we consider these areas, now this is the area covered by the canopies. Now, this area is 1/4 of a circle. So, this is a quarter circle. And what is the diameter of this circle? Of dia d. So, because we have 4 quarter circles, 1, 2, 3 and 4, that is covered in this square. So, we have 4 into a quarter circles, that becomes 1 full circle. Now, the area of the circle is given by pi r square. R is equal to d by 2. So, the area of the circle is equal to pi d by 2 square or pi by 4 d square. Here we saw that the area of the square is given by d square. So, how much of the area of the square is covered by the canopies? So, the packing density is given by the area covered by the circles divided by the area of the square, which is pi by 4 d square by d square, these get cancelled out, is equal to pi by 4. Now, pi by 4, if you convert it into percentage terms, it will be pi by 4 into 100%, which comes to 78.5%. So, the packing density in the case of a square packing comes to 78.5%. Now, consider a hexagonal packing. In the case of a hexagonal packing, you have trees that are arranged at the vertices of a regular hexagon. So, when these trees grow, their canopies will touch each other in a hexagon. Now, this hexagon will further go out and we will also have trees here. Now, the point here is to figure out the area that is covered by these hexagons. Now, if we look at these circles, and we also have a point at the center that is touching all the other canopies, right. So, in this case, if we look at this portion, we have 3 circles that are touching each other. Now, what is this length? Is again d, because it is r plus r. This length again is d, this length again is d. So, essentially what we have here is we have an equilateral triangle that has 3 canopies. That are touching each other. Now, if we look at this portion, the angle subtended here is 60 degrees, because it is the angle of an equilateral triangle. If you take a ray and if you make it go all around it, it becomes 360 degrees. So, what about this sector that is covering only 60 degrees? So, it becomes 60 upon 360 degrees, or 1 by 6 of a circle. So, this region is 1/6 of a circle. Now, in this triangle, we have 3 such 1/6 circles. So, let us call this triangle O1, O2, O3. Now, this triangle has a diameter of, has a side of d. Now, because this is an equilateral triangle, the area of the triangle is given by root 3 by 4 into the side square, which in this case is d square. If we consider these 3 sectors of the circles, so these 3, you have sector 1, sector 2 and sector 3, and all these 3 sectors are 1/6 of a circle. So, we have 3 into 1 by 6 circles, or we have half circle here of dia d. Now, the area covered by the canopies is equal to half the area of a circle of dia d. So, it becomes half into pi by 4 into d square. Now, if you want to calculate the packing density what will that be? So, packing density, this area divided by the area of the triangle. So, it becomes half into pi by 4 d square whole divided by root by 4 d square. D square and d square get cancelled out, 4 and 4 gets cancelled out, and so it becomes pi by 8 into is pi d square by 8, and this thing is root 3 by 4 into d square. So, d square and d square get cancelled out, and this area becomes pi by 8 into 4 by root 3, or when expressed in percentage terms it becomes 90.6%. So, in the last slide we saw that the packing density in the case of a square packing is 78.5%. So, if you consider a square packing, density is 78.5%, whereas in the case of a hexagonal packing, the density is equal to 90.6%. Thus, a hexagonal packing will give us a higher number of trees per hectare of the forest as compared to the square packing, and which is why a hexagonal packing is preferred when we want to extract as much of the wood as possible from the stands. Thank you for your attention. Jai Hind.